So they talk about literals. A literal is something that's hard-coded into the program. What does hard-coded mean? It's written into the program. It's not something that the user types in. There can be numeric literals. There can be string literals. This is an integer literal, right? Apples is equal to 20. Since it's coded into the program, if the end user ever wanted it to have a different number of apples, we'd have to change the program for them. That's why it's called hard coding. Another term for it is a magic number. Why do we pick 20? I don't know. Say you're doing some kind of calculation and in the middle of the code you see a reference to the number 6.022E23. You go, I don't even know what that is. It's a magic number. Well, you know, yeah, we can look it up. It's Avogadro's number using chemistry calculations. But it would have been better if it had been assigned to a variable, given a good name, rather than just used in the calculation as 6.022. Because I bet that you can get a more precise version of it than that anyways. So typically you try to avoid magic numbers. You try to avoid using hard-coded values. Another example would be pi, right? I have a whole bunch of calculations involving pi, and let's just say that I use 3.14159 throughout my code for that. Great, but it's not very precise. Later on, the customer tells me they want more digits of precision, and so I go and I get pi out to 10 decimals rather than 5. And I start going through all my code, trying to find all the places where I use that number, making a change, and on one of them I make a mistake. It would have been better to declare that as a constant up at the top of the program and then just use that constant over and over. Better still would be to find a way to import it so that you could use C++ library version of pi. Let's see if I have that hanging out real fast. Nope, I don't. All right, so this is eventually what our boilerplate might wind up looking like. It's got a whole bunch more things involved. We've always been including IOStream, and we're going to start including string all the time anyways. We might as well start using CMath as well. And if we get math.h and CMath, that's going to cover all of our math needs. We'll have to learn about when you would want to use one and when you'd want to use the other. Some of the strangeness is that Windows by default, or the Microsoft compiler by default, brings in parts of the CMath library, whereas on the Mac it does not. And so for those of y'all who are using a Mac to do your development at home, the code's not going to work the same way as it does here unless you do # include CMath. So we really ought to just be doing that as a matter of course. I'm going to go ahead and modify my boilerplate a little bit because I want it to do string, because we will be using strings an awful lot, and CMath just for the purpose that I told you, so that for the Mac users, when they write their code, it will compile the same way that it does for the Windows users. Now this one, use math defines. Let's Google what that does. Gives us math constants. That sounds like a good thing. So if you # include CMath or you # include math.h, looks like you should only have to bring in one or the other. So maybe we'll get rid of math.h until we find out that we need it. Then you'll be able to get things like pi, m_pi, set to a pretty high degree of precision. Pi is really, about the only one that we use. But also, the square root of 2 and 1 over the square root of 2 and a whole bunch of other constants that I never really thought about ever needing, like 2 divided by pi. But that's the biggie. That's the one that I want to be able to use. So I'm going to add to my boilerplate, and I'll post this in our class notes. The # define, use math defines. Now it's weird that that's enough to get it in, because last time I showed you # define, we gave you the name of the macro and then we gave you the value. Well, you can define a macro that doesn't have any value and it'll still do the trick for some purposes, and the some purposes in this case is to make sure that it gives us the value of pi and the other things that we want. So that's our new improved boilerplate. I'm going to go and put that in to our classes section. Sorry, I should do this later. I realize it takes slightly longer than I thought to do it. That'll do it. All right. Do improved boilerplate. I'll be using this one when I create my next project. This enables us to get the value of the math constant pi, so I won't just have to use 3.14159. I may as well launch Visual Studio in the background knowing that it's coming up and I'm going to need it. So if you type in a number without a decimal point, it's an int by default. There's another data type called a long. I'm sorry that it's got such a silly name. In Java, it's merely called a long, but in C++, it must be even better because it's a long as opposed to a short long. I don't know. But there's two different integer data types. One's 4 bytes and one's 8 bytes. The 4-byte integer can hold a number up to 2 billion. The 8-byte integer can hold huge numbers. But by default, if you type in a literal like that, it's an integer, so it's a 4-byte data type. So if I typed in a number here that was more than 2 billion, it would probably give me a compilation error. It'd probably light it up as red and say that that's not an int, it's too large to be an int. And then there's another way that you can declare it. If there is a decimal point in it, then it's a floating point, but it defaults to the type double, which is the 8-byte, the double-wide floating point. And I can hold the hugest amounts of data of any of these data types. So we'll cover those data types again pretty soon. Just want to get used to the idea that, you know, literals are fine, but if you're going to be using it more than once in your program, you probably ought to store it in a variable and use that instead, which is what they did right here. Apples is equal to 20, and then they can just, you know, modify that value whenever they need to. They don't have to keep typing in 20, 20, 20 all throughout the code. String literals, same thing. Now, it's less common to declare all of your strings in constants and then declare those constants. I mean, then use those constants, but you could. Identifiers. Those are variable names, function names, class names, method names, all of those things. Identifiers are the things you create, not the int, the double, you know, the word if and while. Those are all keywords. Instead, the identifiers are the things we get to make up. So in this code right here, that function name is an identifier. Now it looks like a keyword, right? Because every single program we create has a main method. But we could have changed it. It wouldn't run, but we could have. Apples is certainly not a keyword. It's not built into the C language. Instead, it's one that we made up. You know, it's a variable name that we made up. Return, though, is a keyword. We couldn't change that keyword. Int, we couldn't change that unless we changed it to a different numeric data type. INT, yeah. Using, we would not want to change that. Namespace, we would not want to change that. Right. So there's a lot of things we can't change, but our data variables that we create, we get to pick the names for. And so there's a couple rules for them. Identifier rules. They can be letters, digits, underscores, and dollar signs, but never use dollar signs. Other languages don't support dollar signs. They don't even work for all C++ compilers. So I'm going to kind of backspace over that. Can't see that. They can be upper and lowercase. They can't begin with a digit. So, tax rate, that's a good variable name. Tax rate, that's bad. Tax rate like that, that's good. Tax rate 1980, that's good. 1980 tax rate, that's bad. It's considered modern programming style to do it like this rather than use underscores. That's considered the modern programming style. However, when I'm typing code in up here, I use underscores because I think it's easier for you to type in, and people will always, not everybody, but when you're typing in things that have both uppercase and lowercase, it's real easy to miss making the R uppercase in one place or two places, and then you have a syntax error and we have to figure it out. So all of these variable names are good except for that one because it has a space and it's only allowed to be letters, digits, and underscores. And that one because it begins with a digit. Any other symbol is verboten, forbidden. You can't like put a name like that, right? Because that symbol means something else. It's not part of a variable name. We couldn't do that. Or name question mark. Again, a question mark means something else in the language. Not sure what. I have to think about that. All right. And I've been saying variable names, but function names follow the same rules. You can't create a function that has a space in the middle of it. You can't create a function name that begins with a number. Now, honestly, that would never even occur to you as something that you want to do. So it's not too big a drawback. The keywords. A lot of keywords. We'll know like maybe half of them by the time we're done. And yes, there are a lot more than that, right? It can be an interesting project for yourself to go, okay, you know, it's a new morning, I'm going to learn a new keyword. Go to this chart and, you know, Google up what C++ space break does, or C++ space dynamic cache, right? And then learn each one over time. I could tell you what the vast majority of them mean, but I couldn't show you examples of how to use quite a few of them. You don't have to know what everything means on this list in order to, you know, write a C++ program. It's a good idea to know concepts and to be able to Google them up. So variable name should represent the purpose. That's a good variable name. Just calling it I, that's kind of lame. If I said I is equal to 10, well, what is that? Items ordered equals 10? Much better. Way better. So single letter variable names are kind of dumb. The only reason I use them up here is because they're really easy to type, right? And quite often I'm showing you an example of something that's, you know, devoid of purpose, right? I'm just showing you that, you know, if you're going to add two numbers and store them in a variable, why not just pick I, right? You don't have to pick a long variable name in order to get that example going. So in your code, though, you want to be writing your code in such a way that somebody else who sat down and looked at it, even if they weren't a programmer, would have some concept of what's going on. And if they sat down and they saw items ordered and price as another variable and tax rate as another, they'd know that you're writing a program that, you know, has to do with those concepts. Whereas if it just said IO is equal to 3, that was an abbreviation for items ordered, and P equals 7.32, and that was supposed to be price, and T or TR equals, right? So if you abbreviate your names too much, then they become less readable. And so it's just kind of a trade-off. You don't want to create a variable name that's this long, you know, and has, you know, the Declaration of Independence hidden in its name. But, you know, single letter variable names are kind of lame. You would usually want to avoid them, and I've already explained to you why I demonstrate them up here. So the first character of the identifier, oh good, they took $signs out. Character of the identifier must be an alphabet character or, oh, but when they did that, they put a typo in, and underscore. After the first character, you can use alphabet characters, numbers, or underscore characters. Uppercase and lowercase are distinct. So if you did tax rate with a lowercase r and then you did tax rate with an uppercase r later, then it'd be a syntax error and it would not compile until you found that one and fixed it. Fourth quarter sales, that's a bad one. Oh, now they're going so far as to say that containing a $sign is illegal. Well, that's an overcorrection. It would compile. But you shouldn't, because it wouldn't compile on every operating system, on every version of C++. Microsoft, while being amazingly awesome and providing like just about the best development tool in the business, the Visual Studio, their compiler is a little bit non-standard.
So
surprise, surprise.
$sign?
Just that it can't be used, and it has a specific meaning in other languages.
I mean, it seems like they specifically point out $sign over.
Right, right. Why are they pointing that out? I don't know. Because, like I said, honestly, it does work. So I wish that they had not put this slide in here, except just to show you that it doesn't work. Like, this would be illegal as well. You can't say total sales %, right? The only symbol that's legal is the underscore. So why do they call that out like that? I don't know. Let's go ahead and make our project.
Did it ever have a special purpose before, or was it just a character?
It was a carryover from the basic programming language, where it did very much have a specific purpose. It was how you declared a string. So if I go in and I create and I did string name $sign equals Fred. It'll compile and work. Oh, they've taken it out? No, wait, it's string with a lowercase s, sorry. Uppercase, lowercase, got me. Right, and it actually works, even though that slide said that it's an error. It's not in this because this syntax was how you declared strings in a language called BASIC.
So if you called it the print, you would need to use name $sign or just
right,
name?
if I wanted to write it out, I would have to do name $sign because it's part of the variable. Just like if that was an underscore. If I named my variable name underscore, then everywhere I used it, I'd have to call it like that. So erase $signs. It's completely non-standard. We shouldn't be using it anyways. The book says that it's an error. It's not in this compiler. We could probably find a compiler where it was. It's just another symbol that could be used there. Integer data types. We actually have a whole bunch of different types of ints. Way more than we want to think about. I've been saying that an int is 4 bytes, but there's something called a short int, which is just 2 bytes. It's 16 bits. Like your Sega Genesis was a 16-bit machine, and so was your Super Nintendo. And those can only hold numbers of up to 32,000, much smaller numbers.
Very specific smaller number.
Right, right. But that's because, I mean, we could figure out exactly what that number, where that number comes about. And the reason is because if you have 16 bits, I'm going to set the first one equal to 0 for a specific purpose, and then I'm going to just list them out. 15 one of these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And we wanted to figure out what they were. We've talked about how you would add them up. We would say that was a 1. We would say that was a 2. That was a 4. That was an 8. 16, 32, 64. 1 plus 2 plus 4 plus 8 plus all those bits out to that one. And when you did them all, they would add up to 32767. Or the other way to think about it is if you had this, then that is 32768 right there. So why is that the largest number that it can support? Because they want to allow setting negative numbers as well. And to set negative numbers, they use something known as a sign bit. The sign bit is an agreement that if you have a stream of bits, the first one, if it's 0, means the number is positive. But if it's a 1, it means that the number that follows it is negative. Otherwise, how would you indicate that a number was negative? And so you do lose 1 bit by setting that aside to be your sign bit, but it means that you get negative to positive values. So on our 4-byte data type, the normal int, 1, 2, 3, 4, 5, 6, 7, 8, but it's got 4 copies of that. Again, the first one is set aside to represent whether it's positive or negative. And so it can go from negative 2 billion up to positive 2 billion. If you used a different data type called an unsigned int, where even the first bit was allowed to be used, then you'd never have a negative number, but your number could go twice as large. It's still the same range, right? But if this is 0 and this is 4 billion, right? But you need some of them to be negative, then you could pick it up, move it like that, and then go from negative 2 billion to positive 2 billion. And that's what the sign bit does. So when we see here unsigned, it means that we're allowed to get larger values at the expense of not getting a negative value, right? And so along with int, we have unsigned ints. Along with shorts, we have unsigned shorts ints. And here's where it gets curious. They have something called a long int, which Microsoft has decided is the same size as a regular int. But some other languages say that a long int is an 8-byte data type. And then Microsoft decided that, well, the next one past that is a long int. And it's going to be the 8-byte data type. So a little bit of non-standard there. But in order for us to get our 8-byte data type on Windows using Microsoft Compiler, we have to call our variables long int. If you do that, you can leave the word int off. And so I'll just call them a long. But like this. Long SOL for speed of light equals, and I don't remember the constant, whatever. Well, for one thing, it should not be, I'm just going to call it big, is equal to, right, and it can be a great big number. It can be a number larger than 2 billion. I did not have to say long int, right? But I could have. It accepts the fact that if I do not specify it as being an int, a long is an int anyways. Just like if I say short int si equals 3, I can leave off that word int and it knows. If I say unsigned int, not unsinged, unsigned int ui equals 7, again, I can remove the word int there. Some people use some abbreviations like uint to mean unsigned int. Apparently the C++ compiler is not supporting that. There's probably something we could define that would let that work just as well that it doesn't. So anyways, according to our little hierarchy here, a short holds the smallest amount of data because it's only 2 bytes. An int, the normal kind, holds 4 bytes, so it holds numbers up, to about 2 billion. And a long is much larger.
So,
I don't know how many zeros this is. 3, 6, 9, 12, 15, 18. So a 9 followed by 18 zeros is the maximum value that a long can hold. Yes, sir?
would a double not be included in there?
Number is not an integer type. Otherwise, yeah. Integer or doubles are great because they can hold even numbers that are even longer than longs. But these are all whole numbers, data types. And a floating point data type is a different kind of beast. Because, right, because if you have a floating point type, let's say that we had a single byte that we wanted to hold floating point values. We would have to say, okay, part of this byte is dedicated to the why can I never remember what this is called? The number before the exponent. And then the second part of it is dedicated to the exponent. So you might say, okay, these 4 bits represent this number, the 1, and then these 4 bits represent the exponent. And so we could break it up like that. And maybe, according to our coding scheme, that means 1 exponent 2, right? A 1 followed by 2 zeros, something like that. Well, we've chopped in half. It's very different. This means something completely different if it's being treated as a floating point type than if it's being treated as an integer type. So the standards for doubles is that it's an 8-byte data type like a long, but some of those bits are used to hold the exponent.
Okay.
So they can't be used interchangeably, but they're better in a great many ways for holding large numbers. The only way that they are not better than longs for holding large numbers is that if you're using floating points, you can get floating point rounding errors. Whereas if you're adding integers together, a whole number plus a whole number is always a precise result. If you add 1 plus 1, you're always going to get 2. But if you add 0.1 to 0.1, you're not going to always get 0.2. And that sounds stupid. It sounds stupid as stupid, right? But it's true. And the reason why is just like in our, I don't know why I keep sitting up and standing up. In our calculation, we have data that can't be expressed cleanly, right? Just as simple as 1 over 3. We can't express that in our system. If you try to, I could sit down and write 0.333333 all day. So what do? We either, pick a certain number of 3s that makes us feel comfy, or if you've ever learned that nomenclature where you put a line over the 3 and it means that it repeats endlessly. But that's kind of a hack. There's no way you could represent 0.3 in computer memory if your computer memory is doing base 10. Because it simply could not hold an infinite number of 0.3s. Well, computers, when they're binary, only deal well in powers of 2. So 1, 2, 4, 8, 16, 32, all that's great for whole numbers. But the bits on the other side of the decimal point, if they had like 0.1110, that's the 1 over 2 part, that's the 1 over 4 part, that's the 1 over 8th part, that's the 1 over 16th part, the 1 over 32th part, right? And then you try to add those up to get as close as possible to the value that you're trying to represent. And so it's possible that you could run into numbers that would be cleanly represented in binary, but that would be repeating values in integers. I don't know if that's true, but it's absolutely true that numbers that can be cleanly represented in integers cannot be cleanly represented as binary values. We may be able to demonstrate that. Let's see if we can. Let's see if we can get a rounding error showing. I'm not sure this is going to work, but I want to try it. So in my code, I'm going to declare a floating point variable, and I'm specifically using float, which is an inferior form of floating point, to try to get the error to show up. And so I'm going to say float f equals 0.1 semicolon. And then I'm going to say float g equals f plus f and add it to itself 10 times. So f plus f plus f, right? And so that until you have 10 f's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I probably could have just done 10 times f. But anyways, if each one of these is 0.1, then when we add them all up, it ought to be 1, right? Because that would be 0.1, 0.2, 0.3, 0.4, 0.5, 6, 7, 8, 9, 1.0. So at this point, g should equal 1.0. Let's find out if it does. Float h equals g minus 1.0. And then C out less than G, less than E and DL. And let's put some descriptive text here. Wait, no, it's H that we're curious about, right?
Yeah.
My mistake. So check that out. So C out less than quote H equals end quote less than like that.
So it's going to be 0?
Not going to be 0, but that's what we wanted it to be.
Okay.
Yep. So it got rounding error. It's not a huge error, right? It's a point followed point and then 0 sevens followed by 119, right? Very small number, but it's not precise because it simply cannot convert 0.1 to a binary format without losing some data, because 0.1 in binary is an infinitely repeating value, and so it has to store some, truncated version of it in the memory because it can't use an infinite number of bytes to hold it. And then when it starts using it in math, these little errors can build up like that, which is a drag. And you never get errors like that with integer, with whole data types. So floating point errors like that, rounding errors, are actually an annoying thing to have to deal with. And this is a point for a different logic. But what if I wanted to write a statement like this? If h equals 0, then print something. Well, that's not going to work because it doesn't equal age. It doesn't equal 0. It's pretty close, but it doesn't equal 0. So that we could not write an if statement that would trigger exactly like that. Instead, what you have to do is you have to subtract the actual value from the expected value and then see if that's small enough to be allowed as a match, right? So we might subtract the expected value from the actual value, and if the difference between those two was like 0.001, we might say that's close enough, and we base our if statement based on that. But we don't need to figure that out right now. I'm going to modify this statement so it's just f times 10 and see if we get the same error, so that next time I don't have to type in all those plus h's. No. I can't explain why. So multiplication did not get the rounding off error, but addition did. Well, I'm glad that my first effort was to do that. So of your data types, you have, I guess I could type them directly in here. You have shorts, which are 2 bytes, which go up to about 32,000. You have ints, which are 4 bytes, which go up to about 2 billion. And then you have longs. I'm going to take the S off, which holds huge numbers, 1 followed by 19 zeros. And they are 8-byte data types. These are integer data types, meaning you use them for whole numbers. If you need to increase the capacity of it at the expense of not being able to make it negative, then you stick the word unsigned in front of it. Like you could use an unsigned int and it would go up to 4 billion, it just would not be able to go negative. Then there are also floating point types. There's float, which is 4 bytes, and then there's doubles, which is 8 bytes. These hold much larger values and much more precise, so the rounding errors are less. So always go for the doubles. Don't even ever bother remembering that you could define use the float keyword. You go, oh my gosh, it's using 4 more bytes per data. Well, it doesn't matter, right? These computers have gigabytes of RAM, and the fact that you're using an extra 4 bytes to hold your number is not going to mess it up. But then the question is, why don't you just use longs for everything? And I can't really give you an answer to that except to say that an int is the default data type, and so integer math probably works a little bit faster than that. So I want to confirm my theory that if we made these doubles, we saw that floating point error, and it printed out, now it's much smaller, right? It stood a -16 rather than to the -7. It's a point with 16 zeros followed by a 1, 0.0000001. When there were floats, the error was much, much, much larger relatively. You know, it was a billion times larger, just relatively, right? Because it was point followed by 7 zeros and then a number. So this is the default data type, but you can always use a long if you need it. And this is the default data type for floating point types, and there's no reason to ever use the lesser one. Just like there's no real reason to ever use a short, as far as I'm concerned. You may come up with some usage where you decide, well, you know, I'm just feeling like my numbers are always going to be less than 32,000, and so I'm going to use a short. Nah, just use an int. Just use int by default unless you know the number is going to be larger than 2 billion. So when you define a variable, you can list multiple variables on the same line, or you can split them up. You could do int length comma width, or you can say int length semicolon, int width, semicolon. I prefer this method because you could then go and add comments about each one. Right. So if I had some code that I was writing and I had to do, with some kind of measurements, like, double mass, comma, length, right? That's great and all that. But what if I wanted to instead do this, mass in grams, and double length, right? Length in meters, something like that. If I'm not listing them all on one line, then I can go and add comments for each one as I go and create them. So to me, that's preferred. That doesn't mean that I won't ever do it the other way. If I'm going to just create 5 variables to play with, then I might do that. Int I1, comma, I2, comma, I3, right? Or X, Y, Z, A, B, C, whatever you want to do. You can create multiple variables like that. And if they're not worth commenting like that, then yeah, go ahead and define them all on one line if you want. When you declare them, you can also give them a value at the same time. I could say that I1 is 5, and I2 is 10, and I3 is 20, or whatever, right? Or I could say that the mass is 0. I could say that the length is 1. So-called. That's called initializing, when you provide a startup value for it as you declare the variable. Leaving off this equals 0, this is a variable declaration. You give it a type and a name. But when you put the equals, that turns that declaration into an initialization. So to declare a variable, you give it a type and a name. These are all examples, but here's another example. String S, right? Int I. You can also assign an initial value, which is called initializing. Double D is equal to 3.1, something like that. Later on, if you give it a value, that's called assigning. Like this. I didn't give I a value, so I'm going to give it a value now. I'm going to say that I is equal to 10 divided by 6, right? So this is an expression, and that expression is assigned into I. So what's the difference between initializing and assigning? Well, initialization is just when you put the assignment as you create it. There's nothing fancy. I mean, there's nothing special about it, nothing more magical about doing it that way. You could do this if you felt like it, int x, y, z, and then you could say x, y, z equals 1. That's fine. It's not going to break the code, or you can do it like that, all in one line. There's no reason to prefer one over the other, except if you think that makes the code more readable. You don't have to give every variable you create a starting value. If it's going to be calculated later, I didn't need to give this one a starting value. Some people get paranoid and they want to put everything to 0. There's nothing wrong with that. I use the term paranoid, but there's nothing wrong with that. You could create a list of variables, you could set them all to 0, and then later on you can go and calculate them. But if you don't need that value here, if you're never going to use I before you calculate it, you can leave it off. And in some language compilers, it'll even give you a warning. That 0 is never used. And it's true, because all we did is calculate another value and stored an I, and so it'll flag that line yellow. You have to go and delete that equals 0. Now C++ doesn't do that, thankfully, because I find that a little bit annoying. Items ordered equals 15. Here's an example of camel case. Camel case is when you have the uppercase and the lowercase, with the uppercase in the middle, like a hump. That's why it's called camel. Here we create 3 variables: int checking, unsigned int miles, long diameter. Now the fact that they made miles an unsigned int is just kind of a little bit too fancy, too precious for me. They're saying this value can never be negative, and I want you to be able to go up to 4 billion rather than 2 billion. Okay, fine. If I was worried about the size of it, I would make it a long. I would not depend upon making it unsigned. I can't think of why you would want to do that, but you could. So anyways, and then we set these equal to some values. Checking is equal to -20, miles is equal to 4,000, diameter is equal to that. So integer literals are stored in memory as ints by default. If you need it to be something else, you can tack on an L. That means long. If you need to make it a long, you tack on 2 L's. You go, why would I care? Why would I want to do that? Well, what if you create a long, like the deficit, and you want to initialize it to something, and you say, well, the current deficit is, I don't know, $4 trillion. So that's 4 followed by 12 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's probably going to flag that as a syntax error. Well, it didn't. I'm surprised, because if a number that you type in is an integer by default, that's too large to store into an int. Again, the Microsoft compiler is doing something a little bit different than you might see on another compiler. Which is fine. But since this is larger than 2 billion, it should have underlined it as being an error. And then to make the error go away, we would add long as a suffix to it. Or you could use lowercase, but those look a lot like ones. So don't use lowercase if you need to declare that something is a long. Use uppercase letters. And so that just means 4 trillion, and it's 4 trillion, but it's a number that's definitely larger. I really wanted it to just pop that up. I wanted it to demonstrate that number. Nope, it's just not going to do it. All right, fine. You'll see it in other languages. If you take Java, it'll do it, or if you're on some other compiler other than Visual Studio, it might do it. If you ever get into trouble by typing a number in larger than 2 billion and it underlines it and says that it's an error, you can fix it by putting an L there, or in this particular case, 2 L's there.
So you say fix it. What was it? It just takes the error away. It's still too big for a long.
No, it's not too big for a long. It was too big for an int.
No.
And so since the default data type is supposed to be an int, that should be an unreadable value.
But you set it to a long, so that should fix the issue, right?
Well, but it wouldn't even know what this was in the first place. It's like if this was messed up, then how could it come and later and store to this? But miraculously, it's treating it. I don't need. Let me show it to you in a compiler that I know will make it display the error. That's an extremely good point, and I'm going to backtrack and I'm going to try to explore more, explain why it's not true. And the statement was, well, we're storing it a long, so that makes it okay. And yeah, it does, except for one thing, which is that everything on this side of the equal sign gets done first. You can even write a line of code that looks like that, and it's valid code. It doesn't mean anything, right? I mean, it's not doing anything with that number. It's valid code. Just like if I said D times 2 there, that's totally valid code. It's performing that calculation. It's not storing its result or printing it or anything, but it is a valid calculation. And so this is saying that this 1 trillion, or whatever it is a valid calculation. But we just saw a slide that says that the default data type, if you type it in, is an int, and that's too large to be an int. And so it should be underlining it and showing it to be an error. And if I go to a different compiler that I know, this won't take too long, don't worry, that I know demonstrates the error like that. Let me get it going on and I'll show you. All right, so long debt equals, and I'm going to make it 1 trillion, so I'm going to type it in 12 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And it's underlining it because this is not a valid integer expression. It's too large to be an integer expression, and by default, all numbers without decimal points are integers. But then I can tell it, nah, you're tripping, it's okay. And then by putting that L there, it says, oh, you really are making a long, it's okay. So I'm surprised that we're not having to do that in the Microsoft compiler.
You're just trying to argue with the default.
Right. We're changing it so that it's not, this value here is no longer an int in bytes. It's no longer stored in 4 bytes, that this number is now stored in 8 bytes.
Gotcha.
Does that make sense?
Yes.
Mm-hmm.
Yeah. Okay. And the reason I zeroed in on that idea of it's okay because of what it's stored in, you just have to remember that usually the way the computer works is everything that's done on the other side, the right-hand side of the equal, all of that gets done no matter how long it takes before it'll then copy the value across the equal sign.
But can you just declare the variable you were previously using as a integer is now holding a float?
Yeah, can you? Can we say
Provide
int?
float?
Can we say int weight equals 3.2? This compiler says, yeah, sure, you can do that. But what happens when we write it out? Well, you can't store .2 into an integer. So when I print the weight out, it's going to say that it's 3.
Well, I think my real question here is there a way you can convert it to, say, like a large number from a short to a double, or not a double?
Sure, you can do data conversions. And that's called casting. Say I had a number stored in X. I'm reusing all these variable names. Say I had a number stored in X, Y, Z, but I wanted to put it into a double. I could just do this, and it will fit cleanly.
So now you have 2 variables.
Right, I have a second variable. It's got the contents of that one in it, but what if I just wanted to use this number and treat it like it was a double? In that case, I can do that. Or like you do in Python, this syntax works as well. So I could say, please tell me what 1 divided by that is. Right, something like that. And that takes this value that was an integer and it converts it on the spot.
After that point, is it then a double? Or is it
Nope, it hasn't changed this one.
Okay.
It's like,
Once you declare
it's like your
variable-
interpreter went and translated it into Spanish, but your brain is still, it's still got its original value in English. So it's still an integer here. There's no way you can take, maybe, have you done Python?
Yes.
Yeah, okay, so in Python you're used to being able to do this.
Mm-hmm.
And then later on saying XYZ is equal to the integer value of XYZ. You absolutely can't do that in this language. Once a variable is declared as type integer, it has to remain int. You can't then turn around and store data of a different type in it. And if you try to, it'll round it off. It'll so-called truncate it. So if later on I say XYZ is equal to 2.02, it's going to lose that part of it because XYZ is an int.
So
And it's just,
would it throw an error at you if you just typed in double XYZ?
yes, it will. It will. Right? If I do that and try to build it. Now watch it not. But yeah, okay. There are places where you could get away with redeclaring it. Well, here it's giving me all these warnings, but that is the error right there. Declaring a different base type. I'll show you the one time in which you could do that, and that's if you're in a different context. I'm not absolutely sure this is going to work, but let's see if it does. If you're in a different context, if you've created some, well, that's obviously not going to work. That has made a brand new variable called XYZ, and it is a double, and that's not a syntax error. But any changes to it, like if you say XYZ++ to add 1 to it, do not change the original data. This variable is still out there. And when you hit that closing brace, then this variable, retains its state. If I see out XYZ equals XYZ ENDL, it's not going to print out 3.333 or 4.333. It's going to print out that 1 that we assigned way up here. This one got created kind of in a different memory spot, and as long as we were in that memory spot, any reference to it meant that it was that double containing that value. But as soon as we're outside of those braces, it's like that never even happened, and it's got its original value.
So say you return that value, it's still truncated at the decimal?
Returning is a different matter. If we return anything out of this module, since this module is declared as an int, it will truncate it. But if this is declared as a floating point type, then when we returned it, it wouldn't truncate it.
Okay.
I don't think you can declare main as a double. All right, we've kind of got a whole bunch of statements here that just look pretty dang goofy. That's all right. Okay, so there are other ways you can declare variables. If you want to make it a long, you tack on a couple of L's. If you want to specify it in hexadecimal, you begin it with 0x. So if I ever asked you to tell me what FFAB was in decimal, you could do that. Int mynum equals OX FFAB, and then you could print that out, and we would find out what that conversion was. We specified a number in hexadecimal, but when we print it out, it's going to print it out in base 10. Right, and so that FFAB in hexadecimal is actually equal to that. Like if we had F00 or just F0. I wonder what that is. I wonder what F0 is in base 10. It's 240. FF is going to be 255. Like that. Can't think of that we're going to actually use that in this class. Maybe I'll come up with a reason. I just want you to recognize it. If you ever have to specify a hexadecimal number in a program, this is the common nomenclature for it in a great many programming languages. I'm not sure Python supports it though. Yeah, it does. All right. And if you begin it with a 0, it treats it as octal, which is kind of a weird thing. But if I did XYZ equals 0, 25, to you and me that just looks like 25. Or if I said mynum equals 25, let's do that so we can print it out again. Octal just means base 8. And if I mentioned octal, I didn't go on for about very long because nobody really uses it. But, right, I just set it equal to the value 25, but when it printed out, it came out as 21 because it is octal, because that 0 in front of it said don't treat it like base 10, treat it like something else. So just never prefix any of your numbers with a 0. That'll be the only thing I can say, unless it's a floating point. That's totally legal, right? That would work, except for the fact that it's an int and it can't hold that. But you don't put a 0 in front of an integer and expect it to have the result in which you expect it to be, unless you're expecting it to be octal. So this is 77 in octal. This is FF in hex. I'm not going to ask that on a quiz question. If it burns into your brain right now, great. I doubt we're going to see it again. We're going to need to stop pretty soon. The character data type. Every letter that you type in gets stored as a series of bits. Here's a data type to hold it. Like the letter C. You define it with the word char, character. You give it a variable name, and then you can assign it a value. Note that it's got single quotes around it. Python lets you use single quotes or double quotes interchangeably, whichever you feel that they will work. However, in most of the programming languages that follow the C standard, including this one in Java and JavaScript, if you use single quotes, it means it's a single letter. And if you use double quotes, it means it can hold any number of letters. So string types are declared using double quotes, but single quotes declare specific letters. So if we do this, string last name equals, Roberts, that's cool. But if I want to get a specific character out of it, if I want to just store like the last initial, how about just initial? It would be R, like that. And you would recognize it as being a character because it would have a single quote rather than a double quote. The compiler won't let you mess it up. If you get it wrong, it just won't compile. Right, that's a syntax error, it's already underlined it. And that's a syntax error, it's already underlined it.
Just because you're using the syntax char?
It's because I used the wrong symbol to enclose the data that was being stored in it.
Well, normally you could declare a string with one letter, right?
No.
Double quotes?
You're right, you're right. Why is that an error? Because if I had done that, yes,
Okay.
right, exactly. I was creating, this is just going to complain about because that's purely invalid syntax. If you have an apostrophe, the only thing that can go between the other apostrophe is a single letter. But you're right, double quotes can hold anything, whether it's a single letter or nothing, or everything. Let's fix this back to the way it was. I'm not feeling like our program that we've done so far today is worthy of using as a model for homework, so let's wait to assign homework till Thursday, weather permitting. I mean, I could go look. Let's see if I agree with that statement after I look at something. Nah, I'm okay with waiting until Thursday to have a homework assignment. All right, let's make a Dropbox. Are there any questions over what we lectured? I know that we kind of did circuitous stuff, but the chapter's kind of a grab bag of related concepts. So we kind of just wound up sliding around on them.
So I saw as you were scrolling through there, the second homework was on there, but I can't see it on my end.
Oh.
Yeah, I can't see that.
You're right. Can't see that. That would be why nobody's turned it in. I think I'm going to put a different due date on that. Let's take a look at this again because it hasn't been out in people's eyes. And this description is wrong. Alrighty, if I recall what the homework was, it's in the notes for the other file. I need to create the Dropbox for it. And the homework was to create code that would print out a song lyric or limerick or something like that. And so that was in the notes for Lecture D, but there was no Dropbox to put the homework in. That makes sense that why I was seeing what I was seeing. So I will unlock that. I will give it a better due date of a week from today and put that description in there. Thank you for noticing that. Because some people were giving me this homework and they were putting it into the lecture file because they didn't have anywhere to store it. And I hadn't figured that out. Yeah, so I put a comment, make sure that you get it in the right place, but there was no right place. Thanks.